Tutorial 8, Part 3, Phase Transformation. Phase transformation, nucleation and growth. All phase transformation has nucleation and growth stages, which, for example, recrystallization and green growth, solidification, and solid-solid phase transformation. Let's take solidification as an example. First, the nuclei will form in this homogeneous liquid phase. Then, the crystals, the solid crystals, the solid phase crystals will grow around this nuclei. And finally, those nuclei will be the center of those newly formed grains. And also, green boundary will be formed. Homogeneous nucleation. Homogeneous nucleation is defined as apart from the original liquid state and after transformation, the solid state within the nucleus, there is no other states that may facilitate the growth of these newly formed grains. That's what homogeneous means. For example, the nucleation of pure water. And homogeneous nucleation can be described using the formula here. G is the free energy change. Is described by two terms here. The first term, the first purple term, described the energy necessary to create solid with spherical volume, and basically this solid. And this one, delta G, liquid to solid, is the energy of formation of the solid per unit volume. And definitely this is the volume of the grains of the nucleus. And here is the energy necessary to create the surface, the interface between the solid and the liquid. And this term, gamma SS2L, is the surface energy between the liquid phase and the solid phase per unit area. And we know that per 4 pi r square is the surface area of a sphere. And definitely, this reaction must release energy for it to start, for the nucleation to start, definitely. Let's say if we take the derivative of this equation regard to R to find the critical radius for the nucleation to go indefinitely, then we need to take the derivative, and we got the following equation. And we set this derivative to be 0 and find the R value. Then we can find the critical radius, R critical. And this critical radius describes the minimum radius for the nucleation need to be first at in order for the nucleation to freely go. It is because at a certain point from 0 radius, there is no nucleation or no nucleus. First, the nucleation requires energy, and then afterwards, it will start releasing energy, and which allows the nucleation to grow. And the R value, the critical free energy change, the critical R value is here. If we put this critical R value into the expression for the free energy change, then we get the critical free energy change for nucleation, which is the minimum energy we need to first input into this system for it to denucleate, for it to start nucleate by itself, and which is described here by this vertical line. Using the above discussion, we can explain one phenomena in the physical world, which is the undercooling. Actually, for example, in the solidification of water, energy is first absorbed before the actual nucleation starts. That means water will first go below zero before the ice can actually form. It is because the water needs to absorb the critical free energy required for it to start nucleate. Then that means there will be a slight drop of temperature below the melting point of water, as shown in the picture here. However, once nucleation starts, energy will be released from the solidification process, and temperature is increased back to the melting point, which is also described by this picture. Using the expression defined for the free energy change from liquid to solid is defined as the enthalpy change of formation of the solid minus the melting point times the delta S, which is the change of entropy. At the melting point, this will be equal to 0, and therefore we rearrange the term and we get delta S, change of entropy, is equal to this constant. And for temperature below melting point, we have this free energy change is equal to this expression. And that means at the lower temperature, there will be a larger free energy change and a smaller critical energy change. That means a smaller energy required for the nucleation to happen. And that means at a lower temperature, the nucleation will be easier, as shown in the picture here. The nucleation rate is determined by two factors. The first is the number of stable nuclei, and the second is the frequency of atomic attachment to this nucleus. The first term, number of stable nuclei, is determined by the temperature, and at a lower temperature, there will be more number of stable nuclei. And for B, frequency of atomic attachment, for a higher temperature below the melting point, actually, this will be higher. It is because the frequency of atomic attachment is determined also by the diffusion rate. And their respective equation is shown here. And the total nucleation rate is determined by multiply this term and this term. And here is the expression. And actually, there is an optimal temperature for nucleation by these pictures described. Homogeneous nucleation, as its wording implies, there is a third phase which facilitates the growth of the nucleus apart from the original liquid and the solid phase. And the picture here shows how can we derive the equation for this kind of nucleation. The interface, the surface, is the third phase in this system, and by using a surface tension balance and by putting the equations, the respective equations and respective derivations, we got the heterogeneous nucleation is equal to a term energy for solidification. It is also the volume term. It is here, and a surface energy term, which is here, and times the theta. The theta is determined by the contact angle, and the contact angle, which is the theta as lambda, is between 0 and 1. And by this way, it implies that the energy requires for heterogeneous nucleation is actually smaller than the homogeneous nucleation. For heterogeneous nucleation are easier, and also it needs lower critical free energy change for nucleation than homogeneous counterpart. Heterogeneous nucleation has a higher optimal temperature for nucleation rate than homogeneous counterpart. The first equation here describes the homogeneous nucleation, and the second equation here describes the heterogeneous nucleation. And if we put it together in the same graph, we discover that the free energy change required for heterogeneous nucleation are lesser than the free energy required for homogeneous nucleation, and they are related by the equation here. Here is one example why supercooled water must be distilled water. And supercooled water is defined as temperature below the melting point of water, but the water is still in liquid state. And you may see the following link for such experiment. For water to freeze, it must go through phase transformation, which requires nucleation and growth. For pure water, it removes most of the impurities, and which is also the heterogeneous nucleation size. To freeze, water must go through homogeneous nucleation, which requires much more activation energy, which is the critical free energy change for nucleation. And that means it requires a much more low temperature for the water to freeze in this case than for water containing some impurities. Growth rate. After the formation of the nucleus, they will grow, and finally they will change to the completely new grains. And the growth is mostly dependent on the diffusion rate, because the atoms need to diffuse to the nucleation site for the nucleation site to grow large and larger until they finally becomes the new grains. And that means the growth rate will increase with increasing temperature. And to consider the overall transformation rate, it is also multiplied by the nucleation rate and the growth rate. And there is also a optimum temperature for the overall transformation rate. Time of transformation. Awamir's equation. S rate is proportional to 1 over T, and we define the rate using such definition. And using the Awamir's equation, y is equal to 1 minus e to the power negative kt to the power n. K and n is two time-independent constants for the specified reaction. Y is the fraction transformed, and t is the time elapsed. And how can we define the average rate? As we know that at different time, the transformation rate must be different, as different fractions of those phases has been transformed. And the average rate we defined as the half or the half-life or the time required for the half of the amounts to be transformed to be such definition. And the unit, therefore, is defined as the per second. for this average rate. You can see from the picture here, we define the average rate, or t 0.5 to be here, and the average rate is just the reciprocal of this number. Time dependence of phase changes. As I just mentioned, there will be a time dependence of phase changes, which cannot be observed from the phase diagrams. Therefore, we introduce a new diagram called the time temperature transformation diagram, or in short form, TTT diagram, which you'll have a more detail in part 4. Here is an example of this TTT diagram, and one features for TTT diagram is its x-axis is the time axis. It is in logarithmic scale.